Hey everyone, it's Dr. Walker. Let's go over another example from video 529 on properties of conductors and static equilibrium. This one is called Gauss's Law Revisited. So now that we know about the properties of conductors and static equilibrium, we can use Gauss's law for slightly different problems than what we have done before. In this case, we have a point charge Q equals 2 coulombs is at the center of a hollow metal sphere with inner radius R1 is 8 centimeters and outer radius R2 is 10 centimeters. And the hollow metal sphere has a charge of 5 coulombs. Let's just go ahead and call that Q2. That's going to be the charge on this sphere. It's called the point charge. Let's call it Q1. First, we want to know what is the charge on the inside surface of the metal sphere. So we did a similar problem in one of the your turns. What we have to do is we have to use the property that the electric field is 0 inside a conductor. That's the key. Once we know that the electric field is 0, then what we do is we create a spherical Gaussian surface that is somewhere inside this hollow metal sphere. And if we want to think about the flux going through this Gaussian surface, it's going to be 0 because we said the field is 0. So the flux through this Gaussian surface here, this is part A. The flux through our Gaussian surface is 0 because the electric field is 0. So Gauss's law tells us that this electric flux is equal to the charge enclosed within our Gaussian surface divided by the permittivity of free space, epsilon 0. Look at this Gaussian surface. The charge inside must be 0, right? Because if the flux is 0 and this is a constant, then this right here, it must be 0 as well. So, if we know that Q1 is equal to 2 coulombs, but we know that the net charge inside this Gaussian surface must be 0 coulombs, that means that when the charge is distributed on this hollow metal sphere, it must distribute so that on the inner surface, right here, we're going to have negative 2 coulombs of charge. If we have a total of negative 2 coulombs on this inside surface, then inside our red Gaussian surface, the dashed line here, we're going to have a net charge of 0. So that is the answer for part A. The charge on the inside surface of the metal sphere is going to be negative 2 coulombs. That way, the charge inside the Gaussian surface is 0, which makes the field going through the Gaussian surface 0, which is what we want for a conductor in static equilibrium. Part B, what is the charge on the outer surface of the metal sphere? So we know that the outer surface has a charge of 5 coulombs. And we know that the outer surface, I'm going to redraw it here, it has negative 2 coulombs on the inside. But the total is going to be 5. So we can say it has charge X on the outer surface. And that means that the inner plus the outer surface is going to equal the total charge on that hollow metal sphere. So negative 2 coulombs plus X equals a total charge of 5 coulombs. So that means that X equals 7 coulombs. So that is our answer for part B. If we have negative 2 coulombs on the inside, then we must have 7 coulombs on the outside, so that the total charge on the shell here is 5 coulombs. Let's take a look at the next 3 parts of this problem. So the first 2 parts were asking us about how the charge is going to distribute itself. And then the next parts are going to ask us to find the electric field at different distances from the center. So for this part right here, it says what is going to be the electric field at a distance of r is 3 centimeters. So if R1 is 8 centimeters, so R is 3 centimeters, is somewhere over here. That's our R. What's the electric field at this point? Well, we can use Gauss's law. So Gauss's law tells us that the flux through a Gaussian surface is going to be equal to the charge enclosed divided by epsilon naught. So what Gaussian surface? Well, we're always going to make a Gaussian surface that has a radius equal to the distance at which we're trying to find the field. So our Gaussian surface is going to have a radius r is 3 centimeters. What is the flux through this surface? That's what the left-hand side is asking us. And we know that the field is constant. It comes out of the integral. And then we know that the surface integral here for dA, we're getting the complete surface area of our Gaussian sphere, and that's going to be 4 pi r squared. And then what is the charge enclosed within this Gaussian surface? Well, there's only this Q, which we called Q1 earlier. There's only this Q1 inside this Gaussian sphere. So that's the total charge enclosed. And so now we can solve for E. The magnitude of the field is going to be Q1 over 4 pi epsilon naught r squared. And that is the field that we expect for a point charge. So we just need to go ahead and plug in our values. We're going to plug in 2. And then for 1 over 4 pi epsilon naught, I just usually write the Coulomb's constant. So this whole blue part here is equal to KE. So that's going to be 8.99 times 10 to the 9. And let me just put our Q to the right of it since it was behind it. And then our R squared here is 0.03 squared, or 3 centimeters. And we're going to get about 2.0 times 10 to the 13 newtons per coulomb. So that is how we use Gauss's law. In this case, we didn't really need to use the property that the electric field is 0 inside a conductor, because at this location, we are just inside this region of space, which is, we can think of it as a vacuum, but we're not inside the actual conducting surface. We're not in the gray area. Let's look at the next part. This was part C. Let's look at part D. And for this one, we want to find the electric field at a distance of 9 centimeters from the center of the sphere. R1 is 8 and R2 is 10, so 9 centimeters puts us in between. We want to find electric field here. So we said we're going to create a Gaussian surface that has a radius equal to that distance at which we're trying to find a field, that R. And we're going to write Gauss's law. Always start by writing the full law and then go ahead and make any simplifications. We know that we're always going to have E times 4 pi r squared here. We have the spherical symmetry. And then what is the charge enclosed within our Gaussian surface? Well, we already said that we have 2 coulombs of charge here, and we have negative 2 coulombs of charge here. Our charge enclosed is 0. So the electric field is 0. So we kind of took an extra step there. Sometimes you get so used to doing a routine thing that you don't think about, oh, wait a second, we're inside the hollow metal sphere, we're inside our conductor, so the electric field is 0 inside a conductor. Let's look at the last part, part E. What is the field at a distance of 15 centimeters from the center of the sphere? So now we are well outside of the sphere. Our radius is 15 centimeters. We go ahead and draw our Gaussian surface. Big sphere here. And we set up Gauss's law. And we write E times 4 pi r squared for the left side. And then we think how much charge is enclosed in this Gaussian surface. We have Q1. And then we have the charge of the total metals, the hollow metal sphere here, which was Q2. So the total charge enclosed is Q1 plus Q2. And now we can go ahead and solve for the magnitude of that field. It's going to be 1 over 4 pi epsilon naught, or Ke, times Q1 plus Q2 over r squared. We plug in our values, 8.99 times 10 to the 9. And then Q1 is 2 and Q2 is 5. And then our distance is the 15 centimeters or 0.15 meters squared. So we plug all of these values in, and that's going to give us 2.80 times 10 to the 12 newtons per coulomb. So these were just good applications of using Gauss's law like we did back in chapter 6, but now using the fact that when conductors are in static equilibrium, the electric field inside is equal to 0.